So hello, everybody, and let's talk about the software-defined vehicle, and let's talk about what digital twin and driving simulators can contribute to the software-defined vehicle. I think you agree with me that the industry currently is changing, and it's changing dramatically. You know, when I started in the industry, admittedly, it's quite some time ago, cars were developed according to a mechanical design process. So during this time, there was this phrase, okay, build it, make it nice, paint it, and then add controls. So basically, the development process was driven by the mechanical design, and controls and software development more or less was an afterthought. If we look now where the software-defined vehicle is going, where the industry is going, it's changing dramatically, where you see quotes like software is now the engine of the future, or data is the new gold. So where we're moving from a development process, which was driven from mechanical design, to a software-driven development process. So we're moving from the good old V diagram, which I think we have seen thousands of times, to an agile development process where we want to do continuous integration of new software and continuous deployment. In order to realize a software-defined vehicle, we now have to also think about different vehicle layers. So the basic idea is, and I think most of you're familiar with this, so sorry if I repeat the obvious again. So basically, on the lowest floor, there is the classical vehicle platform, how we know vehicles over decades. Then on the second floor, we want to define or lay out the electronics and the electric architecture. Basically, okay, what kind of sensors do we need? What kind of actuators? What kind of controllers? How do we place these controllers? What control tasks do we do locally? What control tasks do we want to do centrally? And then the idea is, once we have developed these two platforms, then on top of this, we develop software, and we develop this software in an agile development process, which is updated regularly. So basically that your platform then is kept fresh over the years by new functionality or improved functionality. The software or the vehicle then feeds back data, which we use for the vision is it's used for two purposes: to improve or drive software development, and also generate new revenue streams for the ones who participate in the development of the software-defined vehicle. And let me spend some more words with respect to the latter point. So a data-driven development process. I hope this slide isn't too busy here. So we just took this from a publication from Porsche Engineering, admittedly, okay, already some years ago, but the vision of a data-driven development process. So in a sense, you have down here the vehicle. The vehicle is equipped with sensors, and these sensors communicate data back to the data, to a large data lake. You then use this data, complemented by synthetic data, which you derive with digital twins, to drive your software development process. Then The new software you build is then tested and validated. And once it's passing this gate, then you can have an over-the-air update. And again, with this, if you have this process established or realized in your company, then you can update software a lot more regularly, like it is done compared to how it used to be in the traditional development process. So if we look at our continuous or agile development process, basically we have the circle CD, which stands for continuous deployment, and the other circle for continuous integration. So on the right side of this, we have the actual vehicle. The actual vehicle, which is receiving the latest software information, and then the operation is monitored and data is given back to the development team. The development team then plans the next software, code it, build it, and does the continuous testing. This area, this is dominated by the digital twin. So the real vehicle receives the software, delivers data. The digital twin helps to develop the software, and then most importantly, the digital twin governs the continuous testing and release phase. So when we talk about the digital twin, this is more than the vehicle. But on the vehicle side, the digital twin needs to represent the mechanical platform, so suspension, the powertrain, the tires, and so on. Same time, the digital twin also, we need to have digital models of our sensors, of our controllers, of the network. And then we also need to have digital, that's the least complicated one. We also need to have a digital representation of the control software. We need a digital representation of the driver, and we also need digital representation of the road, traffic, or in general of the environment. And these digital twin or twins, they then can be used for the continuous integration and continuous testing. I think we all know, in particular, when we move to autonomous driving, we hear we need to drive 1 million miles, we need to cover a lot of different corner cases, a lot of different weather conditions, traffic conditions, and that's where we use the digital twin in order to continuously test our latest software version. So the digital twin then is used on the development side, what's called as model in the loop. It will be used in a real-time environment for hardware in the loop, and it will be used for the continuous testing and in a software in the loop, like here depicted in the cloud. And I think particular in the later one, there it is important. This is where we do the heavy number crunching, where we look at thousands or millions of use cases and where we want to test whether the new software function is going to work. How? Although the cloud computing is very powerful and we made a lot of progress there, but if we're honest, what question do we answer if we do software in the loop with all these automated tests, which we usually do overnight? The questions we're going to answer is it going to work, or are there corner cases where we need to do some more modification to the software? And will it be safe? What's not being answered is, what about the customer? Is the software I'm going to release, will this provide an exciting experience for our customers? Will the customers be so excited that they're willing also to spend money for an additional feature? Equally important, does this experience represent our brand? So does it drive like a Jaguar or like a BMW or like a Mercedes or like a Toyota? And this is the area where we think, although automatic testing, running all these millions of test cases is important, it's a necessary requirement for software release, but it's not sufficient. Sufficient will be once we get to the point that customers are excited about this. And so when we are at the point to assess the driving experience. When we talk about driving experience, we're talking about three things. We talk about, okay, what's the interaction between the driver and the vehicle? So classical ride handling, NVA, noise, vibration, harshness questions. We also talk about what's the relationship between the driver and the electronic assistance. So whether it's the advanced driver assistance systems or autonomous vehicles. So how smooth and how accepted is the coexistence of a physical driver and the electronic assistance. And thirdly, what's gaining more and more important when we talk about driving experience, it is how is the interaction between the driver and the controls? So the whole topic around human-machine interface. And I think we could do a separate webinar where we just endlessly discuss about pros and cons, about touch screens and knots and buttons. But that's the question which also defines the driving experience. And this is where driving simulators come into play. So that you have digital models of your vehicle and of the environment. And now you put a human in the loop. And now this human drives the car, the virtual car, and then experience how the ride and handling is, how the noise and vibration is, what about the sound, what about the performance of the car. In order to have a realistic driving experience, we need to address 3 points. We need to address what we feel, what we see, and what we hear. So we need to have realistic vehicle models and motion cueing where people sitting in the driving simulator say, yeah, this feels like a real car and it behaves like a real car. But just giving you the right motion won't be sufficient. It also, you need to have a realistic graphical environment so that what you feel and see is in sync and is synchronized. And the same is true for noise and sound. Also, this needs to be synchronized with the other cues. What we provide there in order to realize this for the digital twin is when it comes to the vehicle motion, our solution there is called VI-Car Real-Time. So basically a high-performance, real-time capable vehicle model with all tire models which you need for different driving maneuvers you're doing. So you can comes with predefined vehicle library of predefined models where you simply just have to enter the data, and then you can use this model for offline simulations, for cloud computing, for hardware in the loop, or on the driving simulator. Nowadays, what's also very important is, we need to be able to add control software. We need to be able to model electric components, so electric powertrains, batteries, these kind of things. What's also important is that you are able to use it either as a standalone system or integrated in, for example, controls design software like MATLAB Simulink or others. So with this, with iCar real time, we're taking care of the vehicle motions and vehicle vibration. We advert them as our proposal for modeling the environment and the traffic. So environment, I think you all know this. It's more than the road. You need to have traffic signs. You need to recognize the traffic signs. You need to be able to also model other traffic agents. Although here in this picture, there's only one car, but you need to be able also to have other participants in the traffic, whether these are other cars or pedestrians or animals, so that you can model the complete scenario you want to investigate. And then it needs to look realistic, whether the sun is, I think here the sun is setting, or whether it's raining or snowing, or these kind of things. And lastly, you need to be able to create the right noise and sound. So noise and sound coming either from the road, excitation which is excited through the road, through your powertrain, or through wind noise and other sources. And like we said, important is that all these elements are synchronized with this. You get a very immersive and realistic experience, so that people are able to sit in the simulator and say, yeah, this feels like a real car. I just want to give you one example how such a system is used or has been used. So we have been in the business of providing driving simulators for more than 10 years to the industry. And I just want to give you one example where this was used to develop, admittedly a quite special program car. That's the AMG1, a car where the aim was for the 50th anniversary of AMG, or Mercedes AMG, car with the Formula One engine under the hood, but which is street legal, so you can drive it on the normal roads. And let's just have a look at or listen to a video from AMG.
During a test, we got the measurement data where we can have a look at G's and how the car responds to the driver. The specialty about the Project One cell we see here is we got like torque force feedback, torque machine, the full braking system from pedal to brake pads. Today we got Maro Engel coming around. He won the 24 hours race at the Nürburgring in 2016, so he knows his way exactly around the Nürburgring. With a race driver, you got really reproductive driving, so you can constantly go into the same direction and same spots and analyze changes pretty exactly. They're used to drive these kind of performances, so they give you direct feedback and precise feedback.
Die Beschleunigung ist natürlich schon mega.
Sitting in the car feels amazing. I mean, it's such an amazing project, and when you pull away in the simulator, you feel straight away, you know, the huge power, very high precision. The car is really all about performance, and you can feel that, and it puts a smile on your face.
Okay, so much to the AMG case. I don't know what your conclusion there is, but I really like from this quote are two things. So this race driver was saying, you can feel it, and it puts a smile on your face. You know, race drivers, usually they like to drive real cars. And if you manage to get their testament that you can feel the car in the simulator, and if they enjoy it, then you have been doing something right. So I think the combination there, again, it's the simulator, which can generate the motions which are necessary in the dynamic which is necessary, combined with the detailed digital twin model of the car and digital twin model, what you have seen here. This was the Nürburgring. And simulators have been used for developing the vehicle platform, not only, let's say, for race drivers or race cars like AMG or a sports car or a Lamborghini. Simulators also have been used for, let's say, normal cars, for Ford, for GM, or for Mahindra in India. I think they have been used to help to develop vehicle dynamics as well as improve the NVH characteristics of these vehicles. We are here today to talk about the software-defined vehicle. And there I would like to talk about 3 use cases. I want to talk about intelligent cockpit, active sound design, and the lane keeping assist. Intelligent cockpit, I think that's where we see currently a lot of development for the software-defined vehicles, so the cockpit, the infotainment, all these kind of things. So you can do development there with static images where you have mock-ups of your cockpit, and you can do a lot of development there. Again, driven by the question, okay, will it work? But when it comes to the point of assessing what's the driving experience, I think you need to be at one point in time where you take your intelligent cockpit and either put it in the car and drive the car around the world, or you take your intelligent cockpit and drive in the virtual world. Like you see here, this is a video which we took at the CES earlier this year at the Harman booth. So where they have their intelligent cockpit in this vehicle, and then we combine this with the digital twin here. I think the people from Wolfsburg might recognize it. We're here in Wolfsburg and driving the car when it's starting to rain. Later on, we'll have other traffic participants also. I think if we wait long enough, there will be a truck coming. But in a way, you now get the driving experience, how the intelligent cockpit will behave during real traffic with other cars. And I think with this, you then can better evaluate, okay, what are the things that people like? What are the things where we'll first need to do some more work? You see, here in this case, the cockpit was developed, and now we're doing virtual test drives, in this case, in Wolfsburg. The second thing I want to show you is, okay, what the case if I'm still in the conceptual phase. So I don't have my cockpit done yet. So this is the area where we or customers of ours would use VR and AR functionality. But again, the purpose is, or the main focus is, on evaluating the driving experience. So how will my cockpit, my HMI, behave during real-world driving? So I think, for example, here, we're approaching fast this car. So then I can test, okay, while we are approaching this other car, I can test, okay, if I at the same time wanted to do something on my touch screen, how will this affect the road safety? And so I have, through these driving simulators, I have a lot more realistic opportunity to assess whether people will like my new cockpit, and I also can assess how safe it will be. Let's talk about the second point, active sound design. Again, that's something which is now, I think, nearly standard for all the electric vehicles. So car companies are creating sound, like you see here, example from Hyundai. I should have mentioned this. All the customer examples I'm showing here, there are extended customer presentations available. So these companies presented at our what we call Zero Prototype Summit. So either in Europe or in the US. So if you're interested in diving deeper in one of the other cases, let us know, or Google yourself, Google Zero Prototype Summit, and then the company name, and then hopefully you should find the presentation from there. So again, active sound design. So there are now departments in companies who design a new sound. And then they listen to different sounds and basically have jury evaluation. Okay, which is the one which represents better our brand image, which is the sound which gives me better feedback or immersion, for example, on speed, these kind of things. But at the end of the day, if you just listen to the generated sound, you're missing a major part of this. I think what you really want to hear is you want to drive a virtual vehicle where you can combine the active sound with the wind noise, with the road noise, with the noise coming from your powertrain. So you might have different electric motors in the car, and you want to experience this. Then you want to change, for example, other tires and evaluate the sound. All of this, we believe, you can do a lot more efficiently on a driving simulator than for waiting until you finally be able to drive a car, and you're a lot more efficient to do this on a driving simulator and evaluate these different sounds. That's an example. So on this side, you see you drive on a road. I think here the road has different surfaces. That's hard to see, and then you ride on these different surfaces, and you then combine the digital twin of your car with the sound design software. Here it is QNX, and then you can experience, will customers like this sound, or do I still need to do some more work? The last example I want to talk about is lane keeping assist. So it's one example of this advanced driver assistance systems. And again, let's say, besides touch screens, I think ADAS is also an area where people can discuss endlessly. Just in preparation for today's webinar, my boss shared with me a LinkedIn post where a former auto executive was complaining heavily about the current state of the ADAS systems. Or just at our last Zero Prototype Summit, we had a podium discussions about ADAS or about control software development. And then we had one manager from a car company who said, yeah, I have ADAS experience. I have experience how to turn it off. So that's the first thing I do. So long story short, I think this is still an area when we talk about ADAS where there's still room for improvement in order to get this collaboration between the driver and the electronic assistance right, and to improve this. That's how Ford is doing this. So basically, they use a driving simulator in order to calibrate a lane keeping assistance. If you want to calibrate this lane keeping assist, you need to have a very accurate digital twin. The digital twin is basically the base vehicle. You need to have the steering system modeled accurately with stiction and these kind of things. You need to have a digital twin of your camera model, a digital twin of the roads you want to drive, and you need to have the control software for the electronic power assist steering. You combine all this, then you have an environment where you can now assess the lane keeping assistance. You can look at the different maneuvers. And what was important for the Ford engineers, that they were using the same calibration layout on the simulator like they're using on actual cars. So then the resistance, or basically you lower the resistance from experienced driving test drivers. So if they see the same environment, they're more easily ready to work on the simulator and calibrate the system. One reason I'm showing this here is this is something we're seeing lately more and more. So that driving simulators are not only used to check basically the functional behavior of control systems, but they're also used for calibrate or pre-calibrate control systems. So these were just 3 examples where we think driving simulators can provide assistance to this software-defined vehicle, where driving simulators basically bring the customer back in the loop and give you the opportunity to assess the driving experience. Let's briefly talk about what we feel are critical success factors to be efficient with driving simulators. If you want to put it in one sentence, it's right simulators, right models at the right time. Right simulators means we feel, okay, you need to have simulators which can cover a wide performance range so that they are able to cover the entire frequency spectrum. From all what we have seen and from customer feedback, the wider you cover the frequency spectrum, the more immersive the experience is, the more people will get out of the simulator and say, oh, this simulator drives like it feels like a real car. Your simulator should be able that you can study different attributes, not only controls, but also vehicle dynamics, HMI, NVH, things like this. And then we also feel, okay, the driving, you should have the opportunity to select from scalable simulators. And when you move from one simulator to the other simulator, the software stack should remain the same. So in the meantime, we have provided, so you find simulators from us more than 160 around the world. Right simulators, but if you don't have the right digital twins, then you won't get the right driving experience. So basically, you need to have the right models. You need to have an environment where your digital twin can start with little information, can help you in the conceptual study, but then the digital twin also is able, or you have an architecture that you can refine it. You can add software in the loop. You can add hardware components to this so that you can refine the digital twin according to the questions you need to answer. But from my point of view, the most important thing is you all need this at the right time. So it doesn't help you if you have extremely nice digital twins, but if they are not ready when you need them, then yeah, it doesn't help you. And so basically you need to have a digital development plan where you generate all these digital twins depending on what milestones you want to do, what development gates you want to have, and you need to provide these digital twins to different environments, whether for the people who are doing the evaluation of the driving experience on a simulator, whether there are people who do design, whether this is a mechanical design or software design, and then you need to be able to provide these digital twins also to the cloud for continuous testing and continuous integration. If you do all this, then we believe that the driving simulators can be the collaboration platform. And I think collaboration now, in the age or the coming age of the software-defined vehicle, I feel will be very important again. So what we are seeing, not in every company, but in various companies, is that the people who develop the vehicle platform and who develop the E&E architecture and the folks who develop the software, they are at different locations. Sometimes they're even at different companies. But at the end, you need to bring these things together, because at the end, the customers will drive a car which is a combination of these three elements. And there we believe the vehicle, the driving simulator, can be the ideal meeting point where you come together, also with different suppliers and different users, where you come together and assess the driving experience and decide whether the solution you are developing will excite the customer. So, and then basically you can think about, you define sprints. You define what is it I want to achieve in my next development cycle, which is short. You come together at the driving simulators. We are seeing this, that from time to time, OEMs plus their suppliers come to one of our sim centers, and then they have these sprint sessions where they jointly work on the next version of the development process. With this, hopefully, I gave you a little bit glimpse on what we think, how human feedback can also help in the software development process, in the process of the software-defined vehicle. And there are use cases from different customers or case studies. Driving simulators can help you to drive innovation, to shorten development time, and to reduce the number of prototypes. So with this, I want to close, but just to summarize again, if you could remember just two things from my presentation. So we feel that driving simulators can bring the human in the center of the software-defined vehicle and can help you to evaluate the driving experience at every stage of your development. The second thought I want to leave with you is the digital twins which are used on driving simulators have a very high quality and a strong validation. Because humans have been driving this, experienced test drivers have been driving this, and they realize very quickly if there's something wrong with your digital twin. So in other words, look out for the digital twins models which are used in driving simulators and use them for your continuous testing and continuous integration process. Thanks for listening, and I'm looking forward to your questions.